Good morning, everybody, and welcome to our Astrodynamics Day. I hope that you guys are ready to launch off today because
All
we
right, I
have
want
an
you guys to
amazing day for
level and
you. We have Betsy Fortman, who is going to be leading the day and be with you the entire day. And again, just a reminder, please remain on mute, but we want to get this day started and let's go. Betsy, you ready to take off?
I am ready to launch. Let's do it. All right. So we're here for our astrodynamics, which obviously is one of my very, very favorite labs. And I say that because I'm an aerospace engineer. But I want to know what comes to mind when you guys think about space. What are you thinking of? If you have Slido and are able to, or if you just want to drop it in the chat, teachers, to tell us what your students think about space, we would love to hear it. I don't know. Maybe you're like me and you're wondering, um, are we the only people in the universe? Or maybe you're wondering, does it go on forever and ever and ever? Um, so let me know what you guys think about space and what comes to mind. Are you thinking rockets? Are you thinking satellites? Are you thinking cell phone? I'm curious what comes to your mind. All right, you let us know in the chat or in Slido. We can't wait to see your answers. Monica, what comes to your mind when you hear the word space?
Just fast. Just too big for us, and it's kind of like our day to day, a big day, and just
Yes,
vast is what comes to my mind.
I love that. You know what? We go 17,500 miles per hour to get off of this planet, which is just crazy to me to think about. When you all are answering, you're wondering, does the universe end? Is it going on forever and ever and ever? Or is it at one point going to contract back into us? Can we live on other planets? That's a super huge one. All those movies these days, right? How those asteroids coming at us. And can we go somewhere else if we needed to? And some of you are curious about what the temperature is like in space. I love it. I cannot wait to answer some of your questions today. And of course, you'll be able to ask the Galactic Girl, who is going to be with us later today. And I cannot wait for you guys to meet her. She is outstanding. So if you cannot stay the whole day, come back for her at 12:15, okay? All right, let's get going. This lab was created by an amazing team of engineers. My good colleague Milton and Travis helped to spearhead this along with some amazing interns, Lauren and Katie, you can see here. And what are we going to do today? That might be on your mind, right? We're learning about space. We can't launch ourselves, but guess what? We can launch some vehicles today. And I'm pretty excited that you all get to do that. So we're going to talk a little bit about the space history so that we can understand, how do we do this? How have they done it in the past? How do we take launch vehicles and launch them? How do we get those payloads into space? And then you guys get to build your own rocket, which I think is pretty awesome. All right, so I am an aerospace engineer. My name is Betsy Fortman, and we had a question from you all. That was, how did you decide at a young age to pursue something as complex as aerospace engineering, and what inspired and continues to motivate you in this field? So we had several different high schools out there. We had Archbishop Stepanek, Gilmore High School. We had some other high schools in New York as well. I just want to say thank you for submitting these questions. They are awesome. All right, so for me, I knew I wanted to go in the space program, from a very early age, but I remember saying in the fourth grade I was going to work in the space program. And I kind of knew I couldn't do it. I couldn't get to space, but I knew I wanted to help other people get there. And so I remember very clearly the very year after, in the fifth grade, there was something called Challenger. And Challenger was our space shuttle that, upon launch, ended up exploding. And I remember watching this and thinking, not that, hey, we shouldn't be doing this, but hey, these people right here, the Challenger crew, died for something bigger than themselves. And I absolutely wanted to be a part of it. And I wanted to help take our country even more forward. So that it was a great question from y'all. Keep those questions coming to us. They are amazing. All right. So I went to Purdue University and I studied aerospace engineering. And I started something called a co-op program where I got to work on the F-18 and help put sensors underneath the F-18 and then stick it in wind tunnel tests while I was still in school, you guys. Um, I don't know if you've ever sat in a classroom. You could raise your hands. Have you ever asked, like, why am I learning this? When am I ever going to use this? Anyone? Oh, I see you out there. I'm not alone. High five to you. I promise you, it's like reading a book. You're learning all this information and it becomes a part of you and you get to apply that. I won't go into all the details, but these are the spacecraft that I've worked on over my career since 1995. And I can't wait to share more about space as we go through our day today. As you see, there's actually two types of engineering. You may hear it called aeronautical engineering, astronautical engineering, or sometimes we just use the plain term aerospace. What you'll see is the aeronautical, or the part that's like in our atmosphere. Those things like aircraft. Those are what we would have an aeronautical engineer working on. Now, once you get way up there and you start getting into space, that's when you switch to astronautical. And so, if you can imagine, if you're an aerospace engineer, you're probably doing a little bit of both, getting your launch rocket to go launch into space, as well as to handle your satellites and deploy the space station and all of those good things. So let's talk real quick about our past so we can understand vehicle designs a little bit better, and then we will jump into your build. All right, so what is a spacecraft? Well, plainly, simply, it's a vehicle or machine that is designed to travel to outer space. So that might be here in what we call low Earth orbit or LEO, or it might be beyond LEO. It might be out to Mars. It might be out to Pluto, depending on what kind of spacecraft you're designing. You can see on the screen various types of spacecraft that you can see: the Hubble Space Telescope, the Apollo Lunar Module, the International Space Station are all great examples of spacecraft. But how did this all begin? Do you ever wonder that? So back in 1957, there was this crazy space race. Everyone was like hurrying to see which country would be the first to launch to space. Back in 1957, the Soviet Union at the time launched what we call Sputnik. Sputnik was the first satellite and it was orbiting. And at the time, the US was like, hey, we got to get in this game too, right? So the US then launched into their Mercury program. The Mercury program is what got our humans into space, our Americans into space. And it ranged from 1958 to 1963. You might be familiar with Apollo 13. That was our Apollo era back in the 1969 when we actually landed people on the moon, you guys. How cool. And what's really cool about that is we are now going back to the moon and eventually Mars. After that, we were launching people on Apollo, but all of these vehicles were expensive, right? And so we decided we needed to do something more reusable, something that we could actually use over and over again. And that's where we came up with the space shuttle. So back in the 1980s, we were launching space shuttles. You can see Columbia there, did the very first launch. And Columbia, and we had a fleet of space shuttles that worked until about the early 2000s. Okay. So you can see up there on the screen, we were launching these, and that was great. It came back like an aircraft, looked very much like this. And we could reuse and like replace the tiles that got burned up upon reentry and things like that. But of course, if you guys have old cars, eventually they start breaking down. And so we started saying, hey, we've got to upgrade our space vehicles. And that's where we started switching into the commercial crew program. And you see here in 2021, SpaceX Falcon 9 helped us launch into that particular era. And all this is pretty cool, right? But what's even cooler is what you guys are going to do with it in your careers. I cannot wait. All right. So someone asked, after seeing all that, like, how are robotics used in this field? Okay. So Thomas County, you're out there, I think. You were asking about robotics. Well, it is used all over in this particular field. You can imagine the Mars rover, Perseverance, Ingenuity, the helicopter on Mars. We use robotics to do various parts of inspection on the International Space Station, or you might hear it called ISS. Um, we use robotics in all kinds of areas to do attaching and reattaching of different modules and replacing them in different areas. So you can kind of see here's a robotic arm coming up. And one of the really cool ones down here in this bottom lower left is one of the newer things. It's being created and it's being tested. This is here on Earth that you're seeing this. They're using robotics to build their own solar tower that can be used on other planets, which I think is just so amazing that we have all of these different technologies. And I wanted to make sure we addressed your particular question there. So thank you for that. All right, what are payloads? You might hear us use this term all the time, right? But what does it mean? It's actually anything we're sending into space. So we have these giant launch vehicles, right? These rockets, but only like less than a tenth of it is actually our payload. The very, very tip of it is where our astronauts are going to be sitting. And I'll show you a picture coming up here real soon. But really, so if your spacecraft that we're trying to deploy, any kind of rover, any kind of people are payload too. Isn't that crazy? What's cool is that you guys get to put a payload on your rocket and see how many paper clips for your payload, how much weight you can get all the way to the ceiling. I'm so excited for that. So how do we do this? How do we get payloads into space? Well, here is a quick video I want to share with you because this video, oh my goodness, you guys, this was back in the day when it wasn't normal. Like people weren't always going to space like they do today. I think people get used to seeing us go to space and they kind of forget how exciting it can be. But this is going to show you the Apollo 11 launch. Are you ready? Can I have a countdown out there? Ready? 3, 2, 1, go. And give me a thumbs up if you can hear it. Are you hearing it? Oh, let's see here. No. Let's try again. Oh, great.
T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Tower clear.
We got a roll program.
Wow.
30 seconds.
You guys, that gives me chills every single time I watch it. Like I said, it wasn't normal back then for people going and putting other humans out into space, let alone on the moon. And for the whole country to be watching that is just so incredible. What did you notice in that video? Did you see all that fire? Did you see all that thrust coming out? That is what you're going to be working with today. So as that rocket is going up into space, it's pushing out all of that fuel. And we call that every action has an equal and opposite. I know you know it. Reaction. If you were saying that, you are right. So that's what's going to get us into space. But to get there, we have to go through all these different layers of the atmosphere. So we start down here at the troposphere and we go up through the stratosphere and the mesosphere, the thermosphere, all the way out until we get into the exosphere. What's crazy about that is that you're going to have these different layers that have different densities of air. As you're getting up to space, it gets thinner and thinner. And eventually, once we hit space, you're out in the potentially vacuum of what we would call space there. But that's going to make a difference in your rockets and how efficient they are and how much fuel they're going to need in order to perform. Some of you were asking some questions about that, and they'll either come up in our presentation here or you can ask Camille more about it later today too.
full screen.
All right, so let's get going. What is a rocket? How do we use it? Well, rockets, like I said, this very teeny top is where our payload and our astronauts sit. The rest of this rocket that you see here is all basically the propulsion system, what you're designing today. So how do we store enough fuel? In our case, our fuel is going to be air compressed, right? We're going to push it into that balloon, and it's pushing out of that particular rocket. Typically, we have two kinds of rockets, and we're going to get to that in just a second. I want to show you this question. Teachers, type in the chat, or if you're individually logged in, type in the chat. What do you see that is different about the Falcon 9 rocket? That's the SpaceX one. And the Falcon Heavy. What do you see that's different? And how might this help you as you're building? Oh yeah, Lassiter, you're right. High five to you all. It has boosters on the side. So it has more, in our case, more propulsion tanks, more balloons potentially that you might want to consider. We use the Falcon Heavy to lift really heavy objects, right? So we're going to launch light payloads and maybe our crews on the Falcon 9, which is what SpaceX uses. And then we would launch bigger things like the modules that we're building for different space stations out on something called the Falcon Heavy. And so keep that in mind. If you're trying to put more payload, more paper clips, and get them to the ceiling, do you want more boosters on the side like Lassiter High School said? All right. So the two types of rockets that we typically have are the left-hand side. You can see here that solid rocket engine. So I think of these like the Roman candles. Maybe on July 4th, you guys have lit some fireworks before, and you know that once you light these, those bottle rockets will kind of shoot up, and there's no controlling this. Once they're burning until they're done. So that's kind of what's happening with these solid rocket engines. On the right, you can see there's a liquid rocket engine as well. I potentially like the liquid ones better because you have the ability to control how much fuel and oxidizer you're mixing. You can also shut it down by closing all the valves. But we do use a combination of both of these types of engines when we're doing space flight. So I wanted to share those two with you as you're thinking about how you're going to create your particular rocket. So what are you doing? Here we go. This is your balloon rocket design challenge. I'm going to walk you through a little bit about what you have in your kits. So in your kit, you all are probably having your balloons. Again, you saw Falcon 9 had one big balloon or one big, booster in the middle. But the Falcon Heavy had multiple ones. So I want you to think, am I going to blow up my balloons to put multiple ones together? Or am I going to do this single one and see what happens? There's going to be a trade-off there, and I can't wait to see how how you decide to do it. Some people may want one, some people may want two. One important thing I want you to think about as you're building. So any kind of spacecraft, whether it's something like the space shuttle here, whether it's like our Apollo or in our Orion vehicles, you'll notice something really important, right? Even the satellites, they are all very what we call symmetrical. You can cut it straight down, and that is to balance those forces. And so I'm going to challenge you as you're building your rockets, make sure you're thinking about how to keep things very symmetrical. All right, so we've given you some straws here. I've created a really big straw just to demonstrate, but our straw is meant to be like our launch tower. We're going to take our straw and our fishing wire. You can see we have some fishing wire in your kits. And here I have a bigger string. You're going to basically thread that through and get it tied up to your ceiling. Now, don't panic. If your school says, hey, you can't tie anything to your tiles, no problem. Your school can alter this. You can go ahead and tie it up or tape it up to your door frame. And if that doesn't work, you can decide that you're going to launch horizontally from chair to chair instead. So you just adapt this to whatever works best in your classroom, and we were going to take it and run with it. I cannot wait. All right, so you got your balloons there. You choose how many, and then you have payload materials. So our paper clips are our payloads. How many paper clips can you get on your rocket is going to determine how successful you are. Can you get 3? Type in the chat how many you think you're going to get up to the ceiling, okay? So let's take a look here on a little more detail. All right, so here on our screen, we've got a couple different methods of doing it. Here's kind of our single. You can see that straw here is going to satisfy keeping us going to a straight launch system. And you can see over here, they've secured it with either some tape, some wire, and things like that. I don't want to give too much away, but if you're taping your balloon, think about what might happen to that balloon if and when it changes its shape as it's deflating and inflating. Oh, okay. I see Challenge Prep says 20. I see Lassiter says all of them. Oh my goodness. This is going to be so cool today. I cannot wait. Camille says 30. All right, here we go. There's a design process, and we use this in every engineering design, whether it's building spacecraft or building electric cars, it doesn't matter. We start and we make a design. We're learning what we were trying to achieve. We make a design. Now, I'm not saying just go right in and start building, right? Some of our best designs happen when we've taken a second and planned first. So I want you to think about what you're trying to achieve and how you're going to do it. Maybe even make out a sketch on paper, draw it out what you're trying to do, and then start building. Okay. And then as you build, you're going to find, oh, this isn't working quite right. And you're going to start tweaking things and testing it. All right. And then we're going to deploy it and we're going to have various launches in our wrap up. And so I am so excited for that. A couple of suggestions for you to think about. How am I going to secure it? Do I need some controllability? So maybe you're going to add some fins to your vehicle. Where are you going to place them? Are you going to place them all on one side? Or are you going to do something to balance it out a bit? Maybe you want to stage it where you know you need more than one balloon, but the balloons are heavy themselves. And so you want to get rid of that dead weight beforehand. And so you maybe use one and then release that balloon and then take the rest of your payload on that second. That's called staging. And so I'm just curious, what are you guys going to be doing for that? Here we go. Here are a couple videos. I want to share these with you because it's really important that you kind of see the build, I think, to know how all the pieces kind of go together, and then you get to adapt it. You guys are the engineers today, which is what makes this so cool. So here is Katie, one of our interns, and she is rocking this build. So I'm going to go ahead and show you that video real quick. And notice she's tying all her paper clips together, right? So that's a really interesting concept that you might think about for yours. She's using Scotch tape. All right. And she's getting ready to put her payload. Notice she's evenly distributing it around the balloon or her rocket. And here you can see her tying and putting that fishing line straight through the straws. She's using multiple straws and leaving them full size. I'm curious, are you going to use multiple straws? Maybe you're going to cut one in pieces. I don't know. It's going to be totally up to you. Here you can see how they've attached this particular payload on the side of the rocket. And here.
Hey guys, so today I'm going to show you how to pump up your balloon and keep it closed while you're building your rocket. So start out by placing your balloon on the pump and hold it down with your hand as you use the pump. The next thing you'll do is set your balloon down and start twisting the end. Make sure to hold it closed so that no air comes out as you twist.
This is key. You guys, I, as a mom,
And
just
then
tied
to
mine
keep it
off.
shut, you can
And
use
it's not
tape,
good to do
a
that.
binder clip, or a clothespin to keep it shut. I hope this works for you guys. Good luck!
Awesome. So I'm glad you got to see that because, like I said, the first time I did it, I just tied it off. And of course, then you can't launch it. So I had to use a second balloon in order to do that. If you're using multiple balloons, how are you going to release them to open up those valves to launch at the same time? Think about some of those questions as you're getting ready to design yours.
Hey guys!
And here are a few examples just to give you some inspiration. But you know what? I am excited to see what you guys come up with because I think we have some excellent engineers out there that are going to come up with some even cooler designs than these. In your workbook, you'll have a few links to look at like how a single booster launch would look, how a multi-booster, that means we have more than one, kind of like that Falcon Heavy that you guys were all commenting on in the chat there. See that there are multiple boosters. And then one that actually uses some staging. So I'm going to go ahead and play that staging one because I think that's probably the most difficult concept to understand so that you can see that as well.
Two, one. Oh!
That's staging. That's staging.
Oh yeah. So you saw that the first balloon started. As the first balloon was finished, it lets it go. It drops that dead weight. And then the second balloon takes it to the ceiling, right? That is successful staging. All right, you guys, you have the materials, you have the information. Good luck. I cannot wait to see what you all build, and I'll see you back here in about an hour. Monica, would you like to take it over now?
I'll take it over. The breakout rooms are about to open, and in those breakout rooms, we're going to have our amazing ET staff there. And first of all, round of applause for Betsy. That was an amazing introduction. I hope you guys all are excited to start building your rockets. But we, in our breakout rooms, we're going to have two college mentors with us. We have Annie from the University of Notre Dame, and we have Bryce from the University of Mississippi, who will be here to assist with you all. And we are going to stop the recording and get rolling.